Hello class, we are on to the next section of chapter 12, 12.2. We're going to discuss arithmetic sequences. This is the first classification of sequences of the two that we're going to study. Okay. So an arithmetic sequence has the form of a plus some value, a plus 2 times that value, a plus 3 times that value, and so forth and so forth. The generalized term is a plus n minus 1d, right? So notice that for the first term, there is no value of d being added to the first term, right? The second term is that same first term, but d more, right? The third one is 2d. The fourth one is 3d. So the general is 1 less than the term that you're on times d, right? So we saw this in the last section when we're adding consistently, right, by 2. So for instance, even numbers, if I start at 2, the next one is 2 more, the next one is 4 more from the first one, the next one is 6 more from the first term, because each one is plus 2, plus 2, plus 2, plus 2, plus 2, right? So that's what's going on with d. Each time I'm just adding d to the last value. So if we write that in relationship to the first term, we're just adding multiples of d to that first term. Okay. So the easy way to tell that something is an arithmetic sequence is that every time you are changing by the same amount from one value to the next in your sequence. Okay. So an example, 3, 5, 7, 9, 11, 13, 15, 17. Each time I'm changing by 2, but if we look at it in relationship to the first one, 5 is 2 away, 7 is 4 away, this is 6 away, the next one is 9 away from 3, right? Every time in relationship to the first term. So here, my starting value is always easy to find for the most part if it's given to me in a sequence like this. The initial value is 3, that's my first term, that's my a. The value of d in this case is 2. In order to find the next term, I'm just going to continue adding by 2. For another example, let's say that the sequence isn't given to me, but certain values from the sequence is, right? So the 12th term in the arithmetic sequence is 118, and the 8th term is 146. So find the generalized term in this case. So I don't know what a is, right? But if I follow this formula, I'm looking at the 12th term. Right? So if I have a plus 12 minus 1 times d, which I don't know as well, and I do the same thing for the second equation. So I know 118 is a plus 11 times d because it's the 12th term, so 12 minus 1. I know 146 is the same thing, but for the 8th term, so it's 8 minus 1 times d. So now what I have is 2 equations and 2 unknowns. Okay, so we're past our discussions of matrices. Chapter 10 was all about systems of equations. So at this point, I don't care how you solve these things. In this example, I'm going to use a matrix. Okay. If you want to use the old school algebraic way, you can do that, right? If you want to do substitution method here with this system, you can do that. If you want to do elimination, you can do that, which is nice because both of these have just an a, so you can subtract one equation from the other and solve for d right away. That's nice too. You can use your system of equations and use Cramer's rule. You can do reduced row echelon form. I am going to actually use the inverse, okay? Because it's a 2 by 2 matrix. It's very, very fast and easy to find the inverse matrix. So 7 minus 11 is negative 1 over 4. Swap the main diagonals, change the signs on the secondary ones, and then I'm just going to do my quick matrix multiplication here. And I get 195 and negative 7. So that should make sense to us because the 8th term is more than the 12th term. So that means I'm going down in value. So here I should have a negative 7 for my value of d. And 195 is my starting value of a. So the general term can be found with 195 minus n minus 1 times 7. the nth partial sum of an arithmetic sequence. So same thing, if I took the list of terms and I added them together to get the nth partial sum, can we find a formula for this? Okay, so the nice thing is that this sequence follows, arithmetic sequences follow a very nice pattern. Okay, so what we're going to do is we're going to use an example from an old school mathematician named Pythagoras. So the story as told to me by one of my professors was that Gauss's father was working at home and his son was bothering him. So he tells him, hey, why don't you go over there and add up the first 100 numbers, first 100 integers, and tell me what it is. And the boy comes back shortly within a matter of seconds and tells him the sum. Okay, so that's kind of a very, very popular tale. We'll talk about how he found the sum of the first 100 integers. Okay, so that's going to be our example. Find the sum of the first 100 positive integers. So the way that Carl Gauss did this as a young child, they say he was like 4 or 5 years old, right, was that he rearranged the numbers. He understood that there's a relationship between the numbers from 1 to 100. Okay, if you take 0, the first number, and the last number 100 and add them together, you get 100. If you take the next number 1 and the next number from the end, which is 99, and add them together, you also get 100. 2 and 98, 3 and 97, so forth and so forth. And you do this all the way up until you get to 49 and 51. Okay. And when you add these together, you will always get 100. So from 0 to 49, that's 50 numbers. So you basically have 50 times 100, which is 5,000. And notice we did not use the value of 50. So to 5,000, you just add the number that we didn't use, which is 50. Okay. So then your sum of the first 100 integers is 5,050. Okay. And so that's how the story goes of how Carl Friedrich Gauss developed his manner of adding integers together, right? Creating a partial sum, right? The first 100 partial sums of the integers. Now, we don't really count 0 as an integer, but it was very useful in the reorganization of trying to add these first 100 numbers together. Okay, so there were 100 numbers in our sum. Again, we're not necessarily counting the value 0. This was just a useful reorganization for us in order to add these together. So we have n terms, right? 1, 2, 3, 4, up to 100. If we split them in half, we have n over 2, right? That's what we did here. We split them in half. That's the way that we added this is how we're going to form our sequence. Okay, the nth partial sum is the number of values in our partial sum over 2 times the first term plus the last term, right? So we just add them together and divide them in half. So here the nth term is generalized with a, right? So this a is our first term in the sequence. An is the last term in our sequence. And then we have the n minus 1 over d. So that's how we find the last term if we needed to, as we saw in the last example, right? So for us here, this would be 1 plus 100 times 50, right? Which would give us 5,050. So let's do an example. Let's take a summation, right? So instead of writing, one way to do this would be to take a sequence, right, and then add them together. But let's say that this is how we added them together, right? So in this case, instead of D, I'm using K for my counter, right? So this is arithmetic in form. My A is 2, okay? So it's still A plus some counter of D, right? So this is still arithmetic. Starting value is 2. And then I'm adding -3 each time. So if I want to figure this out, I don't necessarily need to write out the whole sequence. I can just say, oh, I know how summation symbols work. Let me pull out my terms, right? So again, what do we need? We need the first term, we need the last term, and the total number of terms, which I can find. I know my first term is 2. my last term is A7, so I would just plug in A7. So that would be 2 minus 21, okay, or negative 19. And the number of values I have is not 7. If I'm starting at 0, it's actually 8. Okay. My D value here is negative 3, as I pointed out at the beginning, and N equals 8. So I have everything I need, in order to plug this here. I have my N, my first term, and my last term. I actually don't need the D, but it is nice to, point that out, that from each of these things in my sequence, my series, that's what they are, right? This was my A, this is the D, this is the number of terms is one more than this, okay? And I can find my last term by just plugging in 7 here. So when I plug this in, I get 8 over 2, 2 plus this value, negative 19, so I could just subtract them. So my sum would be negative 68 if I added up all of these terms.